I sincerely believed when I prepared these slides that there would be a paper available. If not today, then by the end of the month. I'm not so sure, although I haven't given up hope. The problem is that the results just keep getting better and better. But then that's one problem. The other problem is that every time there's an improvement, a new set of notation is introduced. So I try to keep only one set of notation. You'll see that you'll see, so there's some other problems. Anyway, so this is a talk in HIDA theory, and I'm afraid I have to assume basic familiarity with the structures of HIDA theory, but, well, we'll see. Between now and the end, the next, when the paper finally, well, this is only the first in a series, you know, well, so. Sure. Well, this talk itself is not going to last a quarter of a century. At least that's not. So some notation. There's a lot of notation. F is a CM field over. If you want, you can assume just it's an imaginary quadratic field. You don't lose anything. You assume all primes are unramified above P, although that's also not necessary, but definitely have to be split over F plus. We take an n-dimensional Hermitian space called V, and now there are going to be 4 unitary groups starting from this V. First G1, which is the unitary similitude group, rather rational similitudes in this, of this vector space, viewed as a, well, as a algebraic group over Q. G2 is the same group, but viewed as the Hermitian, the unitary group of the opposite vector space. That is to say, you just multiply the form by -1, and when you do that, when you add the two together, you get a quasi-split unitary group with a maximal isotropic subspace of dimension n, and then G3, just for confusion, is not G1 cross G2, but the intersection with G4. But this similar to somebody should take a few weeks and get rid of these similitudes once and for all, because they add absolutely nothing to the theory. Anyway, each one has an attached Shapiro variety where the signature at the Archimedean place is determined by some sort of convention or tradition, the moduli problem. Now, sigma is the CM type for the field F, and sigma P is the set of all the p-adic places of F plus, and part of the general setup of HIDA theory, or these moduli, is that you get, with some additional choices, a map from the Archimedean places to the p-adic places, and that's going to be called W. So if you have an Archimedean place, you get a p-adic place, automatic. And there's some other conventions in order to make sure that this theory is non-empty, that there is a family. There are ordinary modular forms, but I'll go into that. All right, thanks to, so HIDA gave an axiomatic presentation of HIDA theory, ordinary modular forms, holomorphic modular forms, assuming some axioms that were proved by Lan. So there are, why does it come out like this? So there's a theory of p-adic modular forms on the Augusta variety, which is denoted IG of G4. That G4, remember, is the quasi-split 2n-dimensional unitary group, and that satisfies the Q expansion principle p-adically integrally. So if you want to know what a form is, it's enough to look at its Q expansion at infinity. And then along with that, there is an axiomatic theory of HIDA families of ordinary p-adic modular forms, that's to say holomorphic modular forms. A HIDA family has some data attached. There's a variable weight, so it's ordinary modular forms of a fixed weight or variable weight kappa. And the level has 2 parts. There's the part, there should be a dot here. There was a dot. Oh, yeah, there you go. So K, this is the level away from P, and then this is the level at P, which I sub R is a congruent subgroup in an Iwahori subgroup. And this is the guarantee that you always have forms of finite slope in a sense. Okay, I'm not going to define these things. These are all standard. So a classical point in the HIDA family is another name for an automorphic representation. Then kappa, which has, so there's an index sigma, which corresponds to the CM point in the CM type. It's a sigma tuple of irreducible representations of the corresponding maximal compact subgroup. So at the point sigma, at the element sigma in sigma, the signature of your original Hermitian space V is A sigma comma B sigma. And so the weight is on the one hand an irreducible representation of this. On the other hand, all that really counts is the highest weight of this representation. Okay? Now, here's the compatibility theory. A sigma, B sigma only depends on the p-adic place corresponding to sigma. Otherwise, there's no theory. And then inside the p-adic group, GLN of the corresponding completion, you have a standard maximal parabolic subgroup with the same Levy factor. So this is the p-adic version of this compact group. So these are associated. All right. Still, we haven't got to. We're getting closer to a statement of a theorem, but still there's notation. Now, okay, pi. Now, something that turns out to be natural. The HIDA theory is actually not about holomorphic forms, or part of it's about holomorphic forms, and part of it's about anti-holomorphic forms. So pi is an cuspidal anti-holomorphic automorphic representation of G1, but it's also about holomorphic forms, and that's dual to an ordinary holomorphic cuspidal representation, which is denoted pi flat. And this pi flat has associated weight, so this is still kappa and the associated level. Okay, so there's a lot of the drama of this construction is playing off pi versus pi flat, and a lot of the inadvertent entertainment is trying to figure out which one means when, depending on reading whose version of the paper. So that's the basic object. When you change G1 to G2, according to conventions, this corresponds. This is really important. This corresponds to the Shapiro variety attached to minus V. Is the complex conjugate of the Shapiro variety attached to V. It's to say it's the Shapiro variety attached to V with the opposite complex structure. So that means whatever is holomorphic for G1 becomes anti-holomorphic for G2 and vice versa. At some point, it decided there was absolutely no way to have a consistently rational set of notation for everything. So at various points, it becomes irrational, but it's different. Anyway, so we have pi and pi flat, the same pair of things, but with different personalities. Okay. And now we write pi, we factor pi, 4 parts, 4 important parts. There's the Archimedean part, which is anti-holomorphic. There's the p-adic part, which is the most interesting, the part at a finite set of ramified places, which we don't think about, and then the unramified places, which is where the L function comes from. So this is unramified. This is, and all we need to know is that pi s has some fixed vectors under some fixed level subgroup that's now denoted k sub s. All right. And as for pi p, some more notation. So first of all, we can just imagine there's one p-adic place to simplify, or one pair of complex conjugate p-adic places. Pi w is, well, pi w, let's suppose it's a principal series representation, which is a good thing to suppose. what we do is first, by transitivity of induction, we first induce from the Borel up to the parabolic of type AW, BW, and then we finish the induction. So here, pi AW and pi BW are principal series, respectively, of these two parts. All of this notation, well, you will be tested on this notation in a few wars. Okay. Hecke algebras. So in HIDA theory, the Hecke algebras are very well behaved. They are finite, in fact, free over the appropriate Iwasawa algebra. Now, what we have done by putting this pi here and then forgetting about it, we're saying that we are taking the irreducible component of the spectrum of the Hecke algebra of forms that are congruent to pi, or whose residual Galois representation is semi-simplification, but it's going to be irreducible, is equivalent to the one attached to pi. So these are the deformations, the ordinary deformations of some fixed Galois representation attached to pi. So, but it's all supposed to be ordinary. There's a p-adic base ring, R, that just keeps coming back. So R is now, everything is happening over R. The p-adic base ring that contains, the syntax of this sentence is a bit twisted. It's the component that contains pi of the ordinary Hecke algebra over this base ring. The base ring contains all the relevant Hecke eigenvalues for pi. So now there's an Iwasawa algebra. The Iwasawa algebra has a bunch of variables. The variables are indexed, well, they're n times the degree of the totally real field. In other words, these are the integer points. This is the Iwasawa algebra of the integer points T of a p-adic torus, which is a p-adic version of a maximal torus. You remember we had these GL product over W of GL AW cross GL BW. This torus is contained in all of them. It's a maximal torus inside that. It's a split torus inside that. And the classical points are, so what are the classical points? Remember, classical points are parameters, the Archimedean and then maybe p-adic parameters for automorphic forms. So there's kappa, the same kappa, which is the weight, and then we add a Nebentipus character, which if you don't want to think about it, you can just ignore. So there's a continuous part or an analytic part, which is kappa, and then there's this. It'll take me 25 years. Kappa was the analytic part, that's the continuous part, and then there's some finite part. So these are locally finite characters, or locally algebraic characters of T. So. Wait, I already said that. I believe this is the last before the statement of the theorem. So, as I said, HIDA theory is not only about holomorphic forms, it's also about anti-holomorphic forms, but in the p-adic setting, it's about the dual of holomorphic forms. Now, those of you who have had the pleasure of studying HIDA's papers know that he also looks at forms with finite coefficients, and I find that very confusing. He's taking the Pontryagin dual. So I prefer to look at inverse limits of finite R modules and direct limits of finite R modules. And this is an inverse limit of finite R modules. So this is a module. This is the dual module of the there's a module over the Hecke algebra T, and there it is. And there's a control theorem, which I'm about to explain what this is, that when you specialize at a sufficiently regular weight, then you get something classical. So this, let me explain everything. So this is a finite rank lambda module, this thing, which happens to have an action of this Hecke algebra T. And this can be thought of as the duals of ordinary modular forms of variable weight congruent to our fixed pi, the one that was fixed at the beginning. And the control theorem says that when you specialize, when you take which means taking the quotient by some ideal generated by the difference between generators of t and the value of characters, the t, you get something almost classical, except not quite, because you take the dual. So this thing here, these are ordinary modular forms of, that is the classical modular forms of weight kappa and nebentypus c that are ordinary and then localized at the maximal ideal corresponding to pi. So this is the sort of thing, this object is the sort of thing that occurs in, for example, when you apply the Taylor-Wiles method to HIDA families. This is the sort of thing you look at. This is a free finite rank R module. And so these are things that are supposed to be familiar. And we can simplify the notation. We can drop the nebentypus and just keep the level. And in that case, we have an R instead of a C. All right. And then this fact, which is which ought to be stated more clearly in the literature, but isn't, this t module is actually the inverse limit over R of these finite things for sufficiently regular kappa, which is completely consistent with Iwasawa theory. Okay, now some hypotheses. One could dispense with these hypotheses and get a weaker theorem, but the theorem makes is more appealing if you make hypotheses. So first you assume that T is Gorenstein in the specific sense that it's isomorphic to its R dual as a T module. This is the kind of thing that comes out. This is the kind of thing that comes out of the Taylor-Wiles method. It was proved in this form in some other cases by Piloni, and it's in essentially in one of my papers. And then this is free over T. Now, in the classical situation of HIDA theory, which is elliptic modular forms, the dual module is free over T because it has a generator, which is the leading coefficient of the Q expansion. One doesn't have a Q expansion, but one can prove this in cases, for example, basically when the residual representation is irreducible and the image is sufficiently large. Okay, we've already fixed this set of bad primes, and we've already done this, except, oh, yes, see, look at this. See, here's the notation, and here's another, on this very same line, the notation has changed from one end to the other, and this just keeps happening. There's a minimality hypothesis. So what this means, essentially, or that the whole family has the same singularities at S. So what does this mean? This means that so pi, remember this family corresponds to all these pi primes that are congruent to pi. And if you take the S fixed vectors, this hypothesis is that you get the same R module. So this is a simplifying hypothesis. Again, if you don't want to think about this, you don't have to. There's a slightly weaker statement. It would be even better to think that this is rank 1. Then you don't have to think about it at all. So this is a symptom of the fact that there is not a complete mod P theory of representations of groups of characteristic different from P. There's not a complete for L functions in any case. So, but what this means is that you don't have a chance to raise or lower the levels at primes in S. All right. A theorem. Yes. Okay, there's a theorem. So let XP be the Sertorus for F. So what I mean by that, this is the subtorus of the restriction of scalars of the multiplicative group of F to to Q consisting of the kernel of the norm to F plus. Not the kernel of the norm, whose norm to F plus is contained in Q. So there's just one X, so it's the kernel plus one extra dimension. And then you got an Iwasawa algebra with one extra variable. The following theorem just gives back Katz's construction for n equals 1, where there is no Hecke algebra. So assume we've got the two hypotheses. Then there is a unique element. This unique element, there's something fake about this unique, by the way, you'll see. In the completed tensor product of this Iwasawa algebra for xp with coefficients in R and their chosen Hecke algebra, such that whenever you specialize, what's a specialization? You specialize, oh yeah, well there's more notation that's missing from this theorem, but that's okay. So phi and phi, there's a specialization here. Phi, yeah, all right. Here we go. You take a classical character, that's a Hecke character. A classical character is just a Hecke character of the Sertorus. And you also specialize at your character pi, which should be pi prime. So pi is now should be an unbound variable, but so this pi should be a pi prime, any pi prime congruent to pi. When you specialize at a classical character, Hecke character, and a classical automorphic representation congruent to pi, what you get is this expression, all right, which you're going to see again. So it's a product of a bunch of terms, which I will now explain. If you don't have the Gorenstein hypothesis, what you get is not an element of the actual Hecke algebra, but something of the fraction of the complete ring of fractions. So it's better to work with an irreducible component. And without the minimality hypothesis, there's also a statement. So this is not so important. And in fact, you can even, there are too many variables. Some of the variables are redundant. The variables in lambda xp, all but one of them was already in T. So you can reduce the number of variables. All right. Okay, that's not so interesting. Okay, here's the explanation. So I will start with the easiest terms. All right, here is maybe the greatest disappointment in this theorem. We do not know how to calculate this Archimedean factor. Neither does anybody else, except when the weight corresponds to a scalar modular form. So in this case of scalar modular forms, this was computed by Garrett. It's also it's more precisely in Shimura's book, one of Shimura's books on the topic. All we know is that it's not zero and it's a rational number. Obviously, if you want to know something about p-adic L-functions, you want to. Well, actually, the question is whether you really do want to know this. This is a philosophical question of great interest to me. Okay. At the bad primes S, we just arrange that what's left is the volume term. This is the second letter in the Hebrew alphabet. Well, we ran out of letters. Another problem that has held us up is that we keep running out of letters. And actually, I was trying to find a way to use hieroglyphics, Egyptian hieroglyphics, but they can't. Doesn't seem to be a package for that in LaTeX. So this is a product of p-adic volume factors that is almost certainly equal to 1, but we haven't done the calculation. And then this is the interesting part. This is what tells you that the specialization of the p-adic L function is related to a classical L function. It's a standard L function. So what is the standard L function of pi and chi? I didn't write this down, but pi is an automorphic representation of un. The standard L function is what you get when you take the twisted base change to gln, and then you tensor with the Hecke character chi. So this is, in any case, a standard p-adic L function. Okay, the next. Now the most challenging term. This is the local term at p. So as you all know, or should know, in HIDA theory, in the theory of p-adic L functions, you do not get a p-adic analytic function that specializes without change to some normalized value of the classical L function. You have to replace the Euler factor at p, and I believe that this is a lie. This is a lie. I forgot to. This should be without the factor at p. The factor at p has been replaced. It's the corrected local Euler factor. So, and here it is. It's a product over the primes dividing p. For each, this ord means that it's the ordinary refinement. There's one for each refinement in the theory of p-adic L functions, but this is the ordinary one that gives you a function that essentially in a finite extension of an USL algebra. So there's one piece for A and there's one piece for B. Okay. This is the part that takes the longest. These are, so remember, pi AW, this is pi AW, this is the contragradient of pi AW. Pi AW is a representation of GLAW. So it has an L function given by the Godemont-Jacquet, or the standard L function for GLN. And what you get is some piece of it in the denominator and the dual at a different point in the numerator. Okay, so this is a point S0. And then there's also an epsilon factor. So that's LAW. So this is a GLAWL function, this one too. And then there's another one for B, which is exactly the same, except you replace the A's by B's. Okay? And this takes, the proof of this part takes about 30 pages. It's the largest section in the paper. But it's been done for several years, but what it means is still. All right. Finally, this is the part that, to which I'm particularly attached. It's better to write it in this way. First a C of pi and then this other factor. This is a generator of the congruence ideal for the pi flat isotypic component of the ordinary, the ordinary modular forms. And which is the same as the pi, the pi isotypic component is the same. C of pi and C of pi flat are the same thing. And the term in brackets, well, you've got a ratio of periods. Each of these things is an actual complex number. And this is a ratio of them. And you get an integer, something that's p-adically integral if you multiply it by the congruence ideal. So when I said that there is the statement that there is a unique function is a lie, I mean this. There is no canonical way to normalize these things. So when the product is canonical, but when you write it in this way, you've made some choices. Right. And this is also a standard issue in HIDA theory, that there's no canonical way to normalize. You can normalize the congruence ideal only up to a p-adic unit. Unless somebody tells me otherwise, I think that's a situation. Okay. The fact that there should be one copy of the congruence ideal in the formula is something that shows up in general in p-adic L functions of HIDA families. Okay, so if you don't think about if you don't care about unitary groups, and there's no reason to have a special fondness for unitary groups, but GLN is something that everybody can appreciate. If you take a twisted base change, you get a tempered cohomological automorphic representation of GLN. The word tempered explains why the classical values, which are critical values of the L functions, look like they are at values S0 plus a half. If you take the motivic normalization, they will come out at integers. But if you take it in this Jacques Langland's normalization. It's something else. So pi is cuspidal. If pi is not cuspidal, then it's more difficult than maybe. It's quite interesting, actually, much more interesting to try to prove the Gorenstein hypothesis, because then you can get things like main conjectures for L-functions of p-adic L-functions of tensor products. Now, in the imagination of people who think about these things, this is only a small part of the p-adic function, that analytic function that should be attached to this capital pi. There should be an eigenvariety for all pi and all chi, not only the ones that are ordinary. And these give different branches. And part of the theory is that you see different branches on different unitary groups. Different ordinary. The general picture is that there are some imaginary pictures that there's an eigenvariety attached to this capital pi. And sometimes it has ordinary pieces, and all the ordinary pieces show up on different unitary groups. That's there. The signature determine, right. And it also determine where the special values are critical in the lean sense. Okay, now the proof. The proof is adelic. Proof is well, part of it's adelic and part of it is arithmetic geometry. So let's see. The main part is the doubling method of Piatetsky, Shapiro, and Reiss. And there's an unfortunate tendency to refer to this as, in some parts, as Shimura's method, but of course it's due to Piatetsky, Shapiro, and Reiss, and it's been completely developed in that setting. There's the construction of a general Eisenstein measure, which is analogous to the one that's in Katz's construction of p-adic L functions for Hecke characters. It's due to Ellen Eischen. And she's one of the reasons this has been improving is that over the years she has improved, and now she has a complete, as of this year, she has a complete Eisenstein measure. HIDA theory, as I said, in the study of ordinary modular forms, and the dual theory, which the dual theory has to be interpreted in 3 different ways. So the dual forms, all of these come into the picture. The dual of a holomorphic form is in the first place an anti-holomorphic form by complex conjugation, but it's also by Serre duality. It's top degree coherent cohomology of some different sheaf. But it's also, and this is essential, it's what you get by taking the quotient of HIDA's big Hecke algebra. And then there is something that is so subtle that there's some disagreement among the authors as to just how subtle it is, between complex conjugation period invariance and the pairings between the dual and ordinary forms. Then a very big part is the analysis of the local representation theory at P and infinity and construction of p-adic differential operators that are intimately related to Archimedean differential operators. And finally, as I said, 30-page calculation of the local integrals at P. So that's what goes into this. Now I will try to say a little bit more about some of this in particular. Prospects of improvement. Well, some of us were so exhausted by the long wait that we were unable or unwilling to check that the factors that come out are the ones that are predicted in the conjectures of Katz and Perrin-Riou, but they have definitely the same form, but you want to check that there is a conjecture. Determining this Hebrew letter, which is a silly calculation. Much more remote, determining the factors at S, which involve the mod L representation theory, well, the mod P representation theory of L-adic groups, which is something that's not complete, and the factors at infinity, which are well, there are two ways to go about this. Either calculate an integral that nobody can calculate, or find a way not to calculate the integral. Extension to overconvergent families. This is in the works, and Ellen Eischen is undoubtedly going to turn to this. And then, most intriguing, wall-crossing congruences to relate branches for different signatures. And this is an active theory that's related to Euler systems and height pairings and p-adic height pairings and things like that. And then finally, if you want to wait a few more years, you don't bother reading the paper, because it's all going to be done using perfectoid geometry, and it will be much more complete. But well, one does what one can. So here's the Piasecki-Shapiro-Rallis theory. Piasecki-Shapiro-Rallis have an incomplete theory, but it was completed gradually over the years, and there's a complete statement in a paper of Lepid and Rallis that came out about 10 years ago. All right, so we've got now we're talking about automorphic forms. So pi is our anti-holomorphic automorphic representation of G1. Pi flat is our anti-holomorphic automorphic representation of G2, and we take vectors that it can be factored over the places, Archimedean and non-Archimedean. Okay, this all involves choices, but at almost all places you take the unramified spherical vector, and it's fine. And then we take the tensor product of these two and restrict it to a form on G3, which you remember is basically the product of two unitary groups. Okay? And it's an anti-holomorphic form. Now, what do we do with an anti-holomorphic form? Anti-holomorphic forms are only of arithmetic interest if they can be paired with holomorphic forms. So let's find a holomorphic form, or something maybe close enough. G4, remember, is quasi-split, so it has a maximal parabolic subgroup called P, whose Levy factor is just GLN. There's also this GL1 that we try to ignore. And now, so we take, for M and T, the notation has changed. M is what used to be S0. We take, yes, M comma T goes to, no, this is different. So we have the absolute value of the determinant, the adelic absolute value of the determinant of M to the power n over 2 plus s times this extra factor you can ignore for s varying in C. Now, C, for those of you who are not familiar with this is a non-Archimedean field that plays a very important role in the theory of automorphic forms. Okay? So it has some peculiar properties that for example, the very next board you see. So we've got a holomorphic family of induced representations of the group G4, and now we choose some we choose some functions in this induced representation, and it's set up so that for S, real part of S sufficiently large, you can add them up as you usually add up Eisenstein series, and you get something that's an Eisenstein series depending on this function, this choice of function f. And then this f is not the f for finite. This is just a function f and a complex variable and an element g, right? So one of the things you can do with non-Archimedean fields is you can integrate functions over them. And this is what we get. Here's an integral. This integral depends on our choices. So we get rid of the center, and then we have we get this. Things are set up so that this makes it. By the way, there was this, I think I said that chi was trivial. And if I didn't say chi was trivial, maybe I erased that by accident. Chi, the character, so this is character chi in the original statement. Let's forget about it. It can be just put in, but it just clutters the notation. So we've got an integral that now just depends on S, on our choice of functions, and then our representations of pi and some additional choices. One of the very disconcerting facts about L functions is that they depend on choices. To get them, the L function itself does not depend on choices, but to the integral representations do. It's much worse for p-adic L functions. There's no way you can avoid the choices. Now, if you unwind the integral, we take, so this dns, so I wrote the Eisenstein series in this raw form. I could have included this, but there is some product of abelian L factors, this thing here. So let's ignore that. When we do that, we've got two kinds of objects. So first, there is an Euler product. This is what usually happens when you've chosen the right data, as Piasecki, Shapiro, and Reiss always did. You've chosen the right setup. You write down an integral like this, and what comes out is a product of two kinds of things. First, there's an Euler product, and then there's a global term. The global term in this case is phi flat. This is where one of the periods comes in. Okay. And now, each of these terms is an integral in a local integral, a local zeta integral, in the style of Piasecki, Shapiro, and Reiss that's normalized because one has to do that. Because the choices have to be compensated. So now this, as it's set up, it doesn't involve any choices. Okay, here's what the formula I just had. Oh, that dn of s is wrong. That's absolutely wrong. The dn of s is on the wrong place. The dn of s, this should be here, okay? So if V is an unramified place, so that is to say V is not in S, V is not Archimedean, V is not in the set of sigma p, what you get here is the standard Euler factor. So this is where the last term in the specialization comes from. Okay? So this is the thing you're supposed to be taking a p-adic interpolation of. For V in S or infinity, we get these other factors. And now let's say a word about what specialization means. So there are two ways to understand classical. Classical, first, pi, so remember we were taking, maybe I'd better do something. Is this, yeah. So remember we had this lambda xp tensor over t, and then we specialized it to our r by a chi tensor lambda pi, like pi prime. This is a specialization. So this is the same thing as evaluating. So we have an element of this topological ring, and evaluating it at a classical point means specializing it at a classical character. Okay, specialization at the pair chi pi prime, and the critical value S0 is contained in chi. Okay. The data of chi contains the critical value. So what is it? So classical could mean that chi is an actual algebraic Hecke character and pi prime is an actual automorphic representation. But we have a more restricted version of this. Chi had better be a character such that when you specialize the integral, you get a critical value in the mean sense. So now there's a classification of the critical values in terms of some data that are purely at the real completions of the unitary group. Okay. So let's imagine for simplicity that there's only one real place. So then the Lie algebra of this G4 is a direct sum of three pieces. K4 is a maximal compact subgroup times the center. P plus is the holomorphic tangent space at the fixed point of this maximal compact subgroup in the Hermitian symmetric space attached to the group. and P minus is the anti-holomorphic subspace. So once again, this is all complex analysis for those of you who are familiar with that stuff. So it turns out in this particular setup that P plus just can be realized, identified with n by n complex matrices. Okay, that's convenient. Okay, for certain S, which is now called M, but which should be S0 in the previous notation, we can choose F infinity so that the specialization is equal to a specific differential operator in UP plus times the holomorphic vector in this induced representation. Let's think about this for a moment. I of M is an induced representation. It's some representation of the enveloping algebra of this Lie algebra. This induced representation has an irreducible subrepresentation, which is generated by a holomorphic vector, which we will call F holomorphic. And it is generated not only over the enveloping algebra of G4, but in fact over the enveloping algebra of this P plus, which is the symmetric algebra, because P plus is an abelian Lie algebra. Okay? So this is part of the choice that goes into the Eisenstein series, and this only works for specific integers M, which happen to be, it turns out, that something I proved a long time ago, they happen to be just the ones that, rather the right half of the collection of critical values in Deline's sense. Okay. So if you're only interested in rationality of special values of L-functions, this is what you need to know mainly. At this point, the specialization of the Eisenstein series is nearly holomorphic, and its pullback to G3 can also be chosen to be nearly holomorphic of weight kappa. All right, so this is how we can so remember we had these anti-holomorphic forms of anti-weight kappa, so to speak, or kappa tensor, kappa flat, whatever. And now we want to pair them with something holomorphic, or it's good enough to, and this is something that Shimura invented many years ago, with something nearly holomorphic. All right. Now there are two ways to proceed, and one of them is better than the other. This is what I did in a paper I published in Krella in the 90s. You can choose your D holomorphic so that the restriction is actually holomorphic, and then the restriction is a holomorphic automorphic form on G3, and it pairs naturally with anti-holomorphic forms. So that's one thing you can do. But it's more clever to, turns out, not to do that, but rather to choose something that stays, whose restriction is only nearly holomorphic, but you get a nice formula for the differential operator. Specific, I'll write it down. Powers of minors along the diagonal. And this is classical invariant theory. And this is what Ellen Eischen did. And so what's very convenient is that even though you have the two choices, either choice gives you the same answer when you pair with an ordinary Heatup family. So that's one of the. There are many, I mean, it's 120 pages of paper. There are many technicalities, and these are some of the technicalities that haven't been completely written down. So recall the dual picture. Remember, we have this modular over the Hecke algebra, which is the inverse limit of these finite dual modules. And this is the latest improvement, which unfortunately has not been, I mean, it's not a necessary improvement. Latest improvement, you can identify this phi tensor phi flat with a compatible family of elements, of variable elements. This is in this inverse limit. I won't try to explain how that works. And they all belong to the same automorphic representation. The only thing that changes is the local component at the p-adic places. Okay? And these are explicit anti-ordinary vectors that are used to simplify the calculation of the local factor at p, and they are given by very explicit functions, and the integral is an integral of actual functions. On the other hand, there are explicit local data that are adapted to the p-adic differential operators. And as I say, it's a long calculation. The last step being the Gaudemont-Jacquet local functional equation. Okay, let me back this up. So some theorem is actually used. Let me just say, emphasize that there's a theorem that's actually used to complete the calculation. This is part of the general automorphic theory. And it's how one gets, remember these p-adic factors look in some sense too good to be true because they have half of the factors in the numerator and the other half in the denominator with an epsilon factor. This actually comes out of the Gaudemont-Jacquet local functional equation. Okay. Now for what are HIDA families? So the Igusa variety is a pro-étale covering, not in a sophisticated sense, but in just a pro-finite limit of étale coverings of the ordinary locus in the Shapiro variety. What is the ordinary locus? This is what George Boxer just talked about in the setting of Siegel modular varieties. It's the complement of everything that's not ordinary in the special fiber. So this is a special fiber with no level at P. And then you can get a pro-étale covering of that by trivializing the multiplicative part or the étale part of the universal p-divisible group. The covering group has a name, unfortunately. It's called H0I. It depends on I, and it's just that GLAW cross GLBW, in fact. For G4, the covering group is GLN. And again, we can just think of this as EP if you like. Yeah, there we go. It's what we've already seen. And there's a construction due to HIDA that allows you to start with this Igusa variety using theorems or theorems and hypotheses were proved by Lan, and to look at highest weight modules of this group and to construct families, continuous ordinary families of p-adic ordinary modular forms. Some notation. V. This notation was in the paper already more than 12 years ago. P-adic modular forms on GI. So what is this? Let me just say. So you take VNM. These are the Igusa variety of level n. It has an integral structure. You take functions modulo p to the m. You take the direct limit over the level and then take the inverse limit over the congruence, and here you get something that is topologically interesting. But you only look at the part that is. I mean, you don't really need to know this. This is the part that is fixed. This just says that we only keep the highest weight vectors. In some sense, this is HIDA's method for turning a representation of some high dimension into a character of a torus. The weights of holomorphic modular forms correspond to highest weights of irreducible representations, and as I said, all that remains after you've done this is the highest weights. And so you can define the forms, the ordinary, the modular p-adic modular forms of weight kappa p to be the submodule on which this group acts by the representation attached to kappa. And then classical modular forms of weight kappa are among the p-adic modular forms of weight kappa p. And this is an identity on ordinary forms. This is the control theorem in the holomorphic version. This says that for sufficiently regular kappa, any ordinary form is of integral weight, of classical weight is classical. Okay? And so you get, here's another notation, you get a pairing of the ordinary forms well, I don't have to write it. Pairing the ordinary holomorphic forms with this dual space, which contains anti-holomorphic forms. This is equivariant for the Hecke algebra, or hermitian for the Hecke algebra. And it factors to the ordinary projection and the projection on the connected component through pi, because we've localized it pi. Okay, this is. On the other hand, using Serre-duality, one can identify this thing with a p-adic integral lattice in the anti-holomorphic forms. But that's not natural, because when you take the anti-holomorphic, when you take the complex conjugate of a holomorphic form, you get something that, when it's paired with the holomorphic form, does not give you something that's algebraic. It gives you an algebraic multiple of a period. That's why the periods ends up in the denominators, because you have to correct by that. In this way, the pairing of an equivariant p-adic measure with values in V, the Eisenstein measure is a measure with values in V, with a classical modular form, can be interpreted as a normalized adelic integral. So this sentence is the main thing that happens in the paper. You want to stay in a p-adic. You want to do something p-adic, and this is purely p-adic. You have a p-adic measure. You pair it with something that's a HIDA theory, but because the projections behave in a certain way, what you get, you can interpret as a normalized p-adic adelic integral. And normalized means you divide by periods. Okay, I'm almost there. So here I can say what the Eisenstein measure is. The Eisenstein measure is a measure on this torus, the xp, there's their character chi, and the torus T, which is what one allows you to incorporate the weights. And you get, for each, if you take a p-adic integral of any character of this, you get a p-adic modular form on G4. And now let's see, we are interested in knowing what happens when we take the p-adic integral of a locally algebraic character. And here's what. And notice that the torus does not depend. Here's another curious fact. The torus does not depend on the signature. All the unitary groups have the same torus, but the values are adapted to different unitary groups depending on the character. Okay. All right, let's look at this vector. Let's write down its Q expansion. It doesn't matter what it is. There's a formula for it. That the formula for the Q expansion is mostly in the paper that was published almost 10 years ago by 3 of the authors. It's Q expansion. It runs through positive semi-definite, in fact, semi-definite integral, hermitian forms in some lattice. That's what it says. And Q to the A is a generalization of Q of e to the 2 pi I. It's e to the 2 pi I trace A Z. So using the same methods as Katz, Ellen Eischen defines p-adic differential operators analogous to the real analytic operators that I mentioned briefly, and computes their action on the Q expansions. And then you get a nice formula. Suppose there's only one place. We take a character that's adapted to the signature, which is a kappa. You have an A tuple and an n minus A tuple of decreasing integers. It's an algebraic character. Here's the identity of Q expansions. The integral of it's purely a coincidence. The EIS also it's the beginning of Ellen Eischen's name. Wasn't intended, as far as I know. Although one never knows about these subliminal associations. Anyway, the integral of kappa against this is theta kappa applied to this p-adic differential operator applied to the Q expansion, and here's how it goes. Remember we had, if the Eisenstein series is the sum of C of A times Q to the A, then applying the differential operator replaces C of A by C of A times P kappa of A, where P kappa is the following. This A, this is terrific. A, this is the sort of thing. This is the sort of thing. I mean, this just keeps happening. in the paper. Yes. So there's this A. This A looks slightly different from this A, although from where you're sitting, it's not clear. So you have a square of size A or B. Then here, the p kappa of this matrix is a product of successive minors of the A part, and then successive minors of the D part. And you'll notice that it's set up so that the powers are always positive. If you do not take here, if you tried to use the wrong signature, you would get negative powers of the determinant. And since these things can be equal to 0, you'd be in a lot of trouble. So this it works it's just what it has to be. And this formula is a well-known formula. It comes from, it's a formula of Schur-Weil formula, essentially. Classical invariant theory. Finally, the congruence ideal. Now, to get the actual C of pi to come out, it comes out of the Gorenstein hypothesis. There was a very, what I think is a very instructive chapter, although probably the experts knew this, but were too clever to write it down. There's you get an actual element of T, or more generally, T tensored with the Iwasawa algebra, by pairing the Eisenstein measure with a free T generator of this module. Well, that's just the way it works out. Oh, there is something very important in the about the doubling method that makes this work. The doubling method. The point is that the doubling method, although you can't see it, is equivariant for the action of the Hecke algebra. This is in fact how it got started. It was discovered by Garrett as being equivariant. It takes, if you integrate only over G1, you'll get something on G2 that is in the same representation. Okay, but the generator is not. The point is that the generator is not purely in a single representation pi, unless pi has no congruences. So you have to take integral generators of different pi's and then take differences and divide by their congruences. And this is where the congruence, the generator of the congruence of the maximum, the greatest, biggest denominator that shows up is the congruence module. And that's it. Okay, I guess I have nothing more to say.